A very good afternoon to you all. I'm Krishnya from Graduate School of Engineering, Hokkaido University. Today, I'm going to present on multiscale model for predicting the mechanical properties of cement paste. So our presentation is structured as introduction, model description, results and discussion, conclusions, and finally ongoing works. Let me brief the introduction part. As we all know that the concrete is one of the most widely used construction material in the field of civil engineering, in which cement is the most active ingredient. Basically, cement reacts with water to form a hardened cement paste, which mainly consists of calcium silica hydroxide, porosity, and other hydrates. Among these hydration products, the CSH and porosity are the most dominant component which determine the mechanical properties such as compressive strength, Young's modulus, and Poisson ratio. This CSH is the main binding phase, and also it has high specific surface area with complex pore structure. If we see the formation mechanism of CSH normally formed with two different densities, namely low density CSH and high density CSH. During the early stage of hydration process, the CSH nucleates the outer surface of the clinker minerals, leading to the formation of CSH matrix with low density. In the next stage, the fresh CSH matrix would start forming the space confined by the existing outer layer CSH matrix, leading to the formation of CSH matrix with high density. During the formation of CSH matrix, the pore space exists in the CSH matrix can be defined as gel porosity. At the same time, the pore space exists in the cement matrix can be defined as capillary porosity. As we all know that the theoretical predictions are necessary for almost all engineering applications. For example, the theoretical predictions for the mechanical properties are necessary for structural analysis and design works, selection of construction materials, and also it would reduce the waste of time, cost, material, and manpower compared to that in experimental method. The previous hydration models such as SimHy 3D, HyMOSTRUCT, and DuCom are developed based on these concepts. However, these existing models with accurate prediction mechanism are limited. Therefore, that continues to need to introduce new approaches. Here, I have listed some of the limitations found in previous works. Most of the researchers have considered only the CSH and portlandite for their hydration products. And also, the cement paste is considered as a three-phase material, including unhydrated clinker, hydration products, and porosity. A major research gap found in previous studies is that the CSH matrix is assumed as a single matrix, ignoring the formation of two types of CSH. And also, for the mechanical properties, the porosity is only used for the prediction of mechanical properties. Therefore, here we propose a two-stage model for accurately predicting the mechanical properties of OPC. Let's move to the model description part. This figure shows the overall procedure for this proposed model. The required input parameters are clinker composition, physical properties, mixing proportions, and boundary conditions such as temperature and relative humidity. This proposed work involves 5 major steps. They are cement hydration model, relative humidity model, thermodynamic model, volume fraction, and finally mechanical properties. In this proposed work, we have adapted the cement hydration model which developed by Parrott and Klo. In order to use this cement hydration model, we required the actual relative humidity for the prediction of dissolution of each clinker mineral. Therefore, we proposed a simple empirical relationship for the relative humidity with hydration period. First relationship is for water cement ratio greater than 0.4 and the second one is for water cement ratio less than or equal 0.4. The next step is thermodynamic model. Here we have used a geochemical software called PreQC to perform the thermodynamic calculations. So the calculated dissolution of each clinker mineral from the cement hydration model are used to predict the prediction of hydrates using frequency. After this prediction of hydrates, the results were converted to the volume fraction of each hydrates by using the molar volume, except the CSH. So we have distinguished the CSH matrix into two types of CSH based on this formula. And also, we have used the detailed chemical shrinkage to predict the capillary porosity more accurately. Finally, if we know all the volume fraction of hydration products and capillary porosity, we can predict the mechanical properties by using the multiscale model. Here, we have used the multiscale model, which consists of three hierarchical levels from CSH matrix to cement paste. In level 1, we have considered the CSH matrix. Here, it should be noted that in this stage, we have considered the CSH matrix as two with two different densities. In the second stage, we have considered the CSH matrix with capillary porosity in level 2. The next level, cement paste, which consists of clinker minerals, hydration products, CSH matrix, and capillary porosity. The results obtained from the volumetric predictions are the input parameters for this level 1. And the computed mechanical properties of previous level are used as the input parameter for the subsequent levels. So let's move to the results and discussion part. This figure shows the variation of relative humidity with hydration period for different water cement ratios. As you can see, the predicted result shows a very good agreement with these experimental results. The RH value decreased with hydration period due to the self-desiccation. And also, the rate of decrease of RH is vary with water cement ratio. For water cement ratio less than 0.4, the RH rapidly decreased with hydration period compared to high water cement paste. This slide details the chemical shrinkage prediction. These two figures shows the comparison of chemical shrinkage with experimental results for water cement ratio 0.4 and water cement ratio 0.55. As you can see, the predicted result shows a good agreement with experimental results. This chemical shrinkage increases with hydration time. And also, the higher chemical shrinkage can be obtained in low water cement paste because low water cement paste consists more content of cement paste, which leads to the more hydration process. Therefore, high volume reduction can be obtained in low water cement paste. So next one is the capillary porosity. These figures illustrate the variation of capillary porosity with hydration period for water cement ratio 0.4 and 0.55. And the predicted result shows a really good agreement with experimental results. Initially, capillary porosity is apparently high. Then during the hydration progress, the formation of hydration products continues to fill the existing void system, leading to the denser microstructure with decreased capillary porosity. And also, the capillary porosity increases with increasing the water cement ratio. And this figure shows the prediction of volumetric volume fraction of hydrates. The input parameters are listed here. As you can see, the clinker contents and capillary porosity are high in cement paste initially, and then volume of clinker minerals and capillary porosity decrease as hydration reaction takes place, followed by increase in the volume of hydration products. And these two figures shows the variation of compressive strength with hydration period for different type of cement and different water cement ratios. The proposed model shows a very good agreement with experimental results. This compressive strength increase with hydration period and reduce with water cement ratio. The capillary porosity decrease with decreasing water cement ratio lead to more denser hardened cement paste. And next, this slides details the effect of proposed RH model in the compressive strength. So this figure shows the variation of compressive strength with two different conditions, that is sealed condition and saturated condition. As you can see, the high deviation is observed between the saturated and sealed condition for water cement ratio 0.3. This is because the access to the external water permits higher degree of hydration in low water cement paste, which means water cement ratio 0.3 and water cement ratio 0.4. The variation decreases with increasing the water cement ratio. And also, the effect of RH can be neglected for water cement ratio higher than 0.4, because the external effect of external water is negligible for high water cement paste, as they contain enough water for the hydration reaction. And this figure shows the comparison of Young's modulus with hydration period for water cement ratio 0.4 and water cement ratio 0.55. The Young's modulus increased with hydration period and reducing with water cement ratio, similar behavior to the compressive strength, because the production of CSH is higher in low water cement paste, and also the capillary porosity decrease with decreasing water cement ratio lead to more denser hardened cement paste. This figure shows the effect of involving two types of CSH. As you can see, the predicted results as considering the single CSH matrix shows approximately 50% deviation of compressive strength and Young's modulus for the experimental results by end of the 360 days of hydration. And finally, these are the conclusions drawn from this proposed work. A multi-stage model has been successfully developed using the geochemical program and a hierarchical model to predict the mechanical properties of OPC. From the volumetric predictions, the predicted capillary porosity and chemical shrinkage were successfully validated using the experimental results available in the literatures. From this hierarchical model, the compressive strength and Young's modulus of cement paste have been predicted, which shows a very good agreement with experimental results. And these are our ongoing works. Thank you.